the introduction to the counting module. So as you've been looking down the list of modules, this one might have been puzzling to you because, of course, everyone knows how to count. Of course, the test is not going to ask you, something like count from 1 to 20. The math section, of course, is not going to ask you that. This kind of counting measured on the test concerns problems such as, in how many ways can 4 novels and 3 reference books be arranged on a shelf so that blah, 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 that some kind of condition about the novels are on the outside, the reference books on the inside, or different orders, this sort of thing. So it's about looking at orders and sets and combinations of things. That's what we're talking about when we talk about counting. So we will discuss counting the number of ways to select or arrange a large number of items. Technically, this branch of math is called combinatorics. That's kind of a fancy, scary word, so we just use the simpler word counting. Technically, what we're learning in this module, though, is elementary combinatorics. In this lesson, we'll just discuss a few introductory points. The first concerns the seemingly simple words and or. Now, those look like words from ordinary conversation, but in fact, they are mathematical objects with mathematical meaning. In counting, and as we will see in probability, and means multiply and or means add. That's a really big idea right there. So let's think about this a little bit. If at a fancy dinner you could choose one of 3 meat entrees or one of 2 vegetarian entrees, how many choices of entree would you have? Well, these are the entrees, so you could have any of the 3 meats or any of the 2 veggies. So altogether, what we have are 5 choices. 2 plus 3 equals 5. So the or meant that we add the 2 and the 3. By contrast, if you could choose one of 3 options, now we don't care whether they're veggie or meat or whatever, but we have 3 entrees and we can pick one of 2 desserts to go with it, how many entree plus dessert combinations are there now? So now we have 3 entrees. With any one of them, we could pick dessert number 1. Or with any one of them, we could pick dessert number 2. And so because of this, we notice that altogether there are 6 lines that I've drawn there, so 6 possible pairings. And so here the number of possibilities is 2 times 3. The word and meant that we multiplied the 2 and the 3. So this is a really big idea, a fundamental idea to keep in mind, that or means add and means multiply. Another important idea is listing the items you need to count. So for example, if you have to make a bunch of arrangements, start listing sample arrangements. Now in the test, it's going to be extremely rare that you would be able to solve a counting question simply by listing all the possibilities. Often, as we'll see, there are going to be hundreds, sometimes even thousands of possibilities. So it would be impossible to make a list in any kind of time-efficient way. But listing possibilities is often a good first step that will give you insight into which approach to take. So often if you're stuck in a counting problem, listing the first few possibilities is one way to start thinking about, gee, what method is going to work best here? In summary, counting, or combinatorics, deals with strategies for counting large numbers of combinations and arrangements. The word and means multiply, the word or means add, and remember that listing is a good preliminary strategy that may yield further insights. The fundamental counting principle. This is, as the name suggests, the single most important principle in this entire module, and it really is based on the very simple idea that the word and means multiply. Fundamental counting principle is a general way to approach tasks that can be broken into stages. Suppose we can divide a given task into stages. Suppose the first stage can be done in n sub 1 ways, the second way in n sub 2 ways, and so forth. the total number of ways to do the task will simply be the product of all these numbers. So the number of ways we could do it in the first stage times the number of choices we can make in the second stage times the number of choices we make in the third stage, etc. We just find the product. Very simple. This is the fundamental counting principle. So I realize this is very abstract. Now I'm going to show a few examples. So for a formal dinner, guests have the choice of one of 4 salads, so a choice of 1 of 4, 1 of 5 appetizers, 1 of 12 entrees, and 1 of 4 desserts. And so the whole idea is that at any particular dinner chosen, you'll get a salad, an appetizer, an entree, and dessert. So of the meals like that, how many different possible meals are there? Well, the fundamental counting principle is perfect here because we're in stages. We can treat each course separately, and there's no restrictions here. In other words, any salad can go with any appetizer, they can go with any entree, so there's no restriction at all. So we can just simply multiply the numbers. That's what the fundamental counting principle tells us. So the number of ways to do this would be 4 times 5 times 12 times 4. Well, 4 times 5, of course, is 20. Then multiply by that other 4, that's 80. Well, 8 times 12 is 96, so 80 times 12 would have to be 960. That's the answer. Suppose we have 6 different books that we'll place on a shelf. In how many different orders can we place these books? Well, think about it this way. The various places are stages. Stage number 1 is what are we going to put in the first slot. Stage number 2 would be what are we going to put in the second slot, that sort of thing. Well, in the first slot, I have 6 choices. So when I start out, I have 6 books. I can pick up any one and put it in that first slot. Now here's the tricky part. For the second slot, I've already picked a book. And so that first book is already sitting in the first slot. So when I go to make that choice for the second slot, I have 5 choices left. There are still 5 books available that I could put in that second slot. And so forth on each choice. On each stage, there are fewer choices that I'll have because books have already been put in the slot. So the third book I'll have 4 choices, the second book I'll have 3 choices, the 5th book I'll have 2 choices, and by the time I get to the last book, I'm only going to have 1 choice because 5 books are already going to be in place, and I'm just going to have that one last book, so I really will have no choice at that point. And so n will be 5 times 4 times 3 times 2 times 1. Now we can simplify this a little bit. The 3 times 2 is 6, the 5 times 4 is 20, 20 times 6 is 120, 6 times 12 is 72, so 6 times 120 is 720. And that's how many different orders, that's the number of different orders in which we can put these books. Notice that in arranging any 6 different items in order, the total number of orders is the product of 6 and every positive integer less than it. So that would be 720 orders for any 6 distinct different items with no restrictions. And in general, if we have to arrange n different items in order, the total number of orders is the product of n times every positive integer less than n. We will formalize this in a couple lessons when we discuss factorials. So just keep this in the back of your mind right now. We'll talk about this more formally, and we'll have a special notation for it in a couple lessons. Here's a practice problem. Pause the video, and then we'll talk about this. Okay. A small division of a company with 25 employees will choose a 3-person steering committee consisting of a facilitator, a union rep, and a secretary. So it sounds like 3 different jobs for 3 different people. How many different possible steering committees could be chosen? So it sounds like if Harry is chosen for the facilitator and Sally is chosen for the union rep, that would be different than if Sally is chosen as the facilitator and Harry is chosen as the union rep. So I'll just point out here that the order does matter. If we swap around the people into the different roles, then we have a different steering committee. Well, clearly, if we're picking them at random, For the first choice, for the facilitator, I have 25 choices. Once I pick that person, there are 24 people left I could pick to be the union rep. Once I pick that person also, there are 23 people left for secretary. So now we have to figure out 25 times 24 times 23. Well, that's not too hard. 25 times 24. For this, we'll use the doubling and halving principle. Half of 24 is 12. Double the 25 is 50. Use the halving and doubling principle again. Half of 12 is 6. So we get 6 times 100. That's 600. So now we just have to do 600 times 23. Well, let's think about 6 times 23. 6 times 23, that's not too bad, because I know 6 times 20 is 120, and 6 times 3 is 18. Well, 20 plus 18, that's 138. Now just tack on the last two zeros, 13,800. So there are 13,800 different possible steering committees that could be chosen. So notice that as we're kind of seeing a pattern here with counting problems. We only have a company with 25 employees, but as soon as we start looking at different orders of doing things, we get very, very large numbers. Some of the largest numbers in mathematics come from combinatorics. In summary, the fundamental counting principle says that if the first stage can be done in n one ways, the second can be done in n two ways, then the complete task can be done. It's just the product of the number of ways, the number of choices we have in each stage. That's the fundamental counting principle. If we have to arrange a set of n different items in order, the number of possible orders is the product of n times all the positive integers less than n. And again, we'll formalize that with a special notation in a couple lessons. The fundamental counting principle with restrictions. Many counting problems on the test contain restrictions of some kind. For the test, it's not enough to say something like, put 5 children in order. The test loves to throw in some kind of restriction. This child must sit next to that child, or this child must sit in such and such seat, or so-and-so can't be on the end, something like that. Counting problems with restrictions, that's actually what you're going to be dealing with on the test. When a restriction of this sort appears in a counting problem that can be broken into stages, always start with the most restrictive stage. If more than one stage contains a restriction, then start with the most restrictive, then the next most restrictive, etc., until only unrestricted stages are left. Here's a practice problem. Pause the video and then we'll talk about this. Okay, so we have 7 children with nice alphabetical names. We're going to sit them in adjacent seats. Dahlia must be in the middle chair and George must be next to Dahlia. So that's our restriction. How many different orders can there be arranged? So notice that if there were no restrictions, then the total number of orders would just be the product of 7 times all the numbers less than 7. Okay, that would be easy. But that's not what we're asked here. So we have to think about this. So first of all, Dahlia we're going to put in the middle. There's only one choice for her. Now George has to be next to Dahlia, but George could be on either side. So there's 2 choices for George. Well, once these 2 children are seated, then we can look at the unrestricted choices. The other 5 children are unrestricted, so we'll just do Al next. How many places can Al sit? Well, there are 5 choices for Al. Once Al sits down, there are only 4 chairs left for Betty. And so forth. With each child, there are fewer chairs, 3 for Chuck, 2 for Ed, and then Fran would have to sit in the last chair. And so the fundamental counting principle tells us that we just multiply these numbers. Well, 5 times 4 is 20, and 3 times 2 is 6. Then 2 times 20 is 40. 6 times 40 is 240, and that's the answer. So there are 240 different arrangements that satisfy this particular restriction. Here's another practice problem. Pause the video and then we'll talk about this. In a certain summer school program, there are 5 periods in the day. Each student takes English, math, history, science, and science lab. In how many different orders can a student schedule be arranged given that science lab must immediately follow the science class? Okay, very interesting. So first of all, let's think about these 5 periods. Where could the science class fall? That science class, it could fall in the 1st, 2nd, 3rd, or 4th slot, but the science class cannot fall in the 5th slot because then it would be impossible for there to be a lab after it. So 4 slots are okay, but the 5th slot is not possible for the science class. So for science, there are 4 possibilities. And once we pick science, then the science lab, we have no choice about that. It has to come right after science. So now we pick those 2, so those 2 slots are occupied, and now the others are unrestricted. So for English, we'd have 3 choices, then math, we'd have 2 choices. For history, we'd have 1 choice. Fundamental counting principle tells us we multiply all these numbers together. And of course, this is just 4 times 6, which is 24. There are 24 possible schedules. Counting problems with restrictions, now we're starting to see problems that actually might appear on the test itself. So these 2 practice problems, conceivably, something very much like this could appear on the actual test. In summary, when a counting problem contains restrictions in certain stages, always do the most restrictive stage first. Now we can talk about factorial notation. One mathematical pattern that recurs frequently in counting problems is the product of some integer n with all the positive integers smaller than n. Because this situation occurs frequently, mathematicians have given the pattern its own name and notation. The pattern of n times all the positive integers less than n is called n factorial. Thus 5 factorial means 5 times 4 times 3 times 2 times 1. Well, of course, that would be 20 times 6, or 120. The notation used for this is simply 5 followed by an exclamation point. We read that as 5 factorial. So, 1 factorial would be 1. 2 factorial would be 2 times 1, which is 2. 3 factorial, 3 times 2 times 1, would be 6. 4 factorial would be 4 times 6, which is 24. 5 factorial would be 5 times 24, which is 120. 6 factorial would be 6 times 120, which is 720. Notice we're getting kind of big already. Factorials get very big very quickly. So I'll just point out numbers you don't need to know, but I'll point out that 10 factorial is already more than 1,000,000. 13 factorial is already more than 1,000,000,000. 15 factorial is already more than 1,000,000,000,000. Now I'll just say personally for me, 1,000,000,000,000 is where inconceivably big begins. So 15 factorial is already inconceivably big. So no one is going to ask you to evaluate something like 20 factorial. Really, there's no calculator on earth that could calculate 20 factorial. It'd just be too large of a number. But the test could expect you to know the factors of 20 factorial and to recognize, for example, that 17 factorial or 13 factorial is a factor of 20 factorial. So think about this. 20 factorial is 20 times 19 times 18 times 17, all the way down to 3 times 2 times 1. So we could factor out the 20 and then leave everything else multiplied together. And of course, everything else, that would be 19 times 18 times 17. So that would be 20 times 19 factorial. Now I could factor out a 19, leave all the other factors, so it's 20 times 19 times 18 factorial. Or I could factor out the 18, so now it's 20 times 19 times 18 times 17 factorial. So it's possible to unpack a factorial like this to see some of its factors. So it would be very easy, for example, to see what would happen if we divided 20 factorial by 19 or something like that. So far in counting problems, we have learned that if we have n different items, we can put these items in n factorial different orders. We will make extensive use of the factorial notation in the next few lessons. In summary, that notation, n followed by an exclamation point, which is read n factorial, is the product of n and all the positive integers less than n. Any factorial is divisible by all the integers less than n and all the factorials less than n. So for example, 30 factorial has to be divisible by every number less than 30. It also has to be divisible by every factorial less than 30. And n different items can be arranged in n factorial unique orders. That's the beginning of the use of the idea of factorials in combinatorics. And again, we're going to be using it quite extensively in the upcoming lessons. Counting what you don't want. This may sound like a strange title, so we'll talk about this. This is an interesting concept. Counting is an area of math that sometimes requires out-of-the-box thinking. We have to be a little bit creative. It's all about having the right perspective. And sometimes the straightforward calculation is not the most efficient. Sometimes it's even prohibitively long. So far, a lot of what we've been learning are very straightforward, direct calculations, and those are great in simpler problems. But in slightly harder problems, those would just take too much time. In this video, I'm going to discuss a creative approach that can simplify some of these slightly harder counting problems. So the method I'm going to talk about here involves shifting the focus on what is asked. Suppose we have n total items. Now, if there are no restrictions at all, the total number of orders is n factorial. We can just put those n items in any possible order. Suppose a restriction is given and we want the number of arrangements that meet that restriction. We have already talked about the way to count arrangements obeying many simple restrictions. Now, for a more complex restriction, here's another way to think about it. Every arrangement of the total n factorial, so we have n factorial total orders that we could put the items in, some of those will obey the restriction and some of them won't. And so let's just say we know n factorial is the total number of arrangements. That's the total number disregarding any restrictions. R is the number of arrangements that obey the restriction that we want. And let's just say that Q is the number of arrangements that do not obey that restriction. Well, certainly it's true that R plus Q equals n factorial. In other words, every possible order must be either an order that obeys the restriction that we want or an order that doesn't. Well, we have this simple equation, and we can simply solve this for R. And so this suggests another way of finding R, another way of finding the number of arrangements that obey a particular restriction. This other way means that rather than count the ways that do obey the restriction, we're going to count the ways that don't obey the restriction. We're going to count what we don't want. That's what Q is. And it's always easy to find the total number. The total number, disregarding any restrictions, the total number of orders is n factorial. And so we'll count the ones that we don't want and subtract that from n factorial. That's the basic idea of this. Here's a practice problem. Pause the video and then we'll talk about this. Okay, this is a relatively simple problem. We almost could just write out the solutions here. It's so simple. And I will say that using the direct methods we have learned, we could do this. Counting all the arrangements that meet this restriction, it would be a little more time consuming. It would be a little more difficult. As we're going to see, there's an incredibly efficient method available with this new approach. So first of all, if we just disregard that restriction, what are the total numbers of orders? Total number of orders, 6 factorial, is 720. So if there were no restrictions at all, there would be 720 ways that those 6 kids could sit in order. So we're going to count the arrangements that don't meet this restriction. In other words, we're going to count all the arrangements with Jackie and Marilyn right next to each other. Okay, the ones that do not obey the restriction. And it turns out that's much easier to count. Think about it this way. We could have them right next to each other on the far left, or 1 seat over, or 1 seat over, or 1 seat over, or 1 seat over. And so those 10 ways, those are the 10 places that we could seat Jackie and Marilyn if they were required to be next to each other. With any of these 10 arrangements, the 4 empty seats could be filled by an arrangement of any of the, the 4 remaining children in any order. So for any one of these, we have 4 factorial, or 24 possibilities for the other children. And so it's just 10 times 24, 240. That's Q. So there are 240 arrangements that would not be allowed by the restriction. Well, we know the total number is 720, so the ones that are allowed, now we can simply subtract. The allowed restriction should be the total number of orders, 720, minus the 240 that are not allowed. And that gives us 480, and indeed that's the correct answer. That is the number of arrangements that obey this restriction, the number of arrangements in which Jackie and Marilyn are not seated next to each other. Notice that the prompt question contained a restriction involving the word not. That can be a clue that thinking about this alternate way might be true. If they want to know the number of orders in which such and such is not true, it might be easier to count the ways in which it is true. Now that's a general rule, but sometimes when we have to count something that is true, we might need to see that it would be easier to count it when it isn't true. And so again, this is a very funny thing about counting. Counting is a lot about pattern matching. It's a lot about sizing up a problem and getting an intuitive sense for it. There's not a formulaic way to decide what kind of pattern is going to work, but the more you get a sense of counting problems, the more you'll have a sense of this. So I'm going to give you a counting problem now where this is true, where it's going to be easier to count something that isn't true. Here's the practice problem. Pause it, and then we'll talk about it. Okay. Harriet has 6 novels she wants to read, one of which is Emma by Jane Austen. She plans to create a reading list of 4 of these novels for an upcoming trip, and different orders count as different lists. How many reading lists are possible if Emma must be on the list? Okay, so we actually could count this. And it wouldn't be that bad to count it, but let's talk about how to count it in this alternate way. The big insight is that it might be easier to count all the possible reading lists without Emma. So the total number of lists, so we have 6 novels. So for the first novel on the list, I have 6 choices. Second, 5. Third, 4 choices left, and the last, we have 3 choices left. So 6 times 5 times 4 times 3. That's the total number of lists without any restriction. Total number of possible lists of 4 novels in a row. So let's see. 6 times 5 is 30. Then I'm going to do 4 times 30 is 120. And then 3 times 120 is 360. So that's the total number of possible reading lists if there's no restriction at all. Without Emma, we can make an ordered list of the 5 remaining books. So for the first book, I'd have 5 choices. For the second book, I'd have 4 choices, then 3, then 2. 5 times 4 is 20, times 3 is 60, times 2 is 120. And that's the value of Q. That's the value of the restrictions that do not, the orders that do not obey the restriction that we want to obey. So the total number of lists with Emma is going to be the total possible number minus all the lists that are without Emma. So that's going to be 360 minus 120 is 240, and that's the answer. If you see that you're able to do this trick, counting the cases that you don't need, then it will save you time. As you practice, pay attention to which method is employed in the solution. Often, especially in Magoosh problems, we're going to show the solution that is most efficient. And so if we've chosen to
to follow this to count the restrictions that do not obey, count the arrangements that do not obey the restriction, then ask yourself, why was that choice made? And that, in fact, is even a great ticket to send in. I don't understand why in the solution they chose to do it this way rather than that way. Excellent questions to ask. If you are asked to count how many arrangements obey a restriction, it may be easier to count the ones that do not and subtract them from the total. So certainly one clue is the word not. Another clue is if there's a restriction that is just focused on a single item, this single item must be included, then it might be easier to count all the ways that that single item is not included. So far we have discussed counting arrangements in which you've been assuming that each of the n items is different, that we have n unique items. And this is certainly natural when the individuals are human beings. Each human being is different, and each human being is unique. Sometimes we have to arrange sets in which we're talking about objects, and some of these objects are identical. And this requires a special approach to calculation. Consider this problem. We're going to talk through this problem. A librarian has 7 books to arrange, 4 different novels, and 3 identical copies of the same dictionary. How many different orders could these 7 books be put on the shelf? All right, well, let's think about how we're going to approach this. Think about it this way. Suppose we temporarily treat the 3 dictionaries as if they were 3 different books. We'll call them D1, D2, and D3. Then we could put all 7 books in 7 factorial different orders. All right, that much is clear. Now let's think about those arrangements. Here's one typical arrangement. Let's just say J, K, L, and M. Those are the 4 novels. And so I put them in this order. That's just a random order with the 3 dictionaries and the 4 novels spread in. Now consider all the arrangements with the 4 novels in the same place and then just the 3 dictionaries rearranged. And so we'd have all these possibilities. Again, these are 6 sets. In all of them, the 4 novels are in identical places and the 3 dictionaries are arranged in different orders. And of course, there are 3 factorial or 6 different ways to arrange those 3 dictionaries. That's why we have 6 cases here. Now, we temporarily were treating those 3 dictionaries as if they were really different, but they're really identical. And all 6 arrangements on the previous slide would look identical. In other words, for all 6 of them, we'd see 3 dictionaries in the same place because it doesn't matter what order we put the dictionaries in. Of the 7 factorial total arrangements, we could group them 6 at a time into groups like this, and all 6 in the group would result in an identical arrangement of books on the shelf. So our number, 7 factorial, is actually 3 factorial too big. In other words, it's 6 times too big, and therefore we have to divide by 3 factorial. So 7 factorial divided by 3 factorial. We'll write out the factorial. We can cancel some factors. We just get 7 times 6 times 5 times 4. 7 times 6 is 42. 5 times 4 is 20. 20 times 42 is 840. And so that would actually be the number of orders in which we could arrange the 4 novels and the 3 identical dictionaries. Notice that in a set of n items, there were b identical items, and the total number of arrangements with those b identical items is n factorial over b factorial. That's an important rule. Suppose the collection of n items contains more than one set of identical items. For example, suppose of the n items, there could be one group of b identical items. They're all the same as each other. A different group of c identical items, all the same as each other. And yet another group of d identical items, all the same as each other. Then the total number of arrangements we would just divide by b factorial, c factorial, and d factorial, by the numbers, by the individual numbers of identical items. Some sources call this the Mississippi rule because of its application to this question: how many different arrangements can we make of the 11 letters in the name of the U.S. state Mississippi? And of course it's tricky because there are so many identical letters in the name of the state Mississippi. We have only one M, but we have 4 I's, we have 4 S's and we have 2 P's. And so we'd have to take 11 factorial, divide it by the 4 factorial for the 4 I's, divide it by 4 factorial again for the 4 S's, and divide it by 2 factorial for the 2 P's. So here's a practice problem of this sort. Pause the video and see if you can do this on your own. Okay, a librarian has 5 identical copies of Book A, 2 identical copies of Book B, and a single copy of Book C. In how many distinct orders can he arrange these 8 books on a shelf? Well, we know that we're going to take the 8 factorial, which is the total number of orders, divide it by 5 factorial for the 5 identical copies of A, and divide it by 2 factorial for the 2 identical copies of Book B. So that's going to be 8 factorial divided by 2 factorial times 5 factorial. I'm going to write out all the factors. I can cancel all those factors in 5 factorial. I can also cancel the 2 with the 6 to get a 3. So I get 8 times 7 times 3, 8 times 21, which is 168. And that's the answer. In summary, if in a total set of n items b are identical, then the total number of distinct arrangements is n factorial divided by b factorial. If in the set of n items b are identical, a different group of c are identical, and a different group d are identical, then we divide n factorial by the product of all those individual factorials. Remember, listing and counting can also be helpful. So if you start to list out some, then it might give you the idea of how to set this up. Often an important approach in counting problems. In this video, we will make explicit something we were doing in calculations in the previous video. We're going to make it explicit and expand the idea a little bit. When a method of counting yields repetitions, that is, the same thing is counted more than once, we have to divide by the total number of possibilities by the time each item was counted. So that's what we're doing in the previous video. How would the same thing get counted more than once? Well, one way, of course, is if we have identical items, and so when we put those identical items in different orders, you can't tell. But another way has to do with orders, whether we care about order or not. Remember that our fundamental approach so far has employed the fundamental counting principle, which analyzes outcomes one choice at a time so that order matters. Order automatically matters when we're using the fundamental counting principle. If we're only concerned about the final element selected and the order doesn't matter, then different orders of the same item constitute repetitions of the same thing. And so this is where we can start the conversation about order. And in a counting problem, it's always important to be aware, are we concerned about order or not? And if we're using the fundamental counting principle, we're automatically going to do the calculation that corresponds to caring about order. In this video, we're going to analyze some of these situations from the perspective of the fundamental counting video. In upcoming lessons, we will talk explicitly about combinations and ways to compute them. So a combination is what we're counting when we don't care about order. And so we'll talk more about that in upcoming videos. But right now, it's very important to understand that everything in counting, including permutations and combinations, fundamentally comes from the fundamental counting principle. The fundamental counting principle is the big idea, and everything else in counting is dependent on that idea. So here we're going to jump in with a fundamental counting principle approach. Suppose there is a room of 20 people, and each one will shake hands with the other person. How many handshakes occur? One way to approach this is to realize that each one of the 20 people shakes hands with 19 other people. One might think the number would be 20 times 19, but that would be too big. It would count every handshake twice. In other words, that would count me shaking hands with Elliot, and it would also count Elliot shaking hands with me, but that's only one handshake. Elliot and I shake hands, and it doesn't matter which person there's not like one person as the starting point in a handshake. Just two people are shaking hands. And so 20 times 19 would count everything twice. It would count it once as one of my handshakes and once as one of Elliot's handshakes, and so that would overcount. And so we actually have to divide by 2 to get the correct answer. 20 times 19 divided by 2, and of course that's 10 times 19, which is 190. Here's a practice problem. Pause the video and then we'll talk about this. Okay. In geometry, diagonal of a polygon is a segment from any vertex to any non-adjacent vertex. For example, a diagonal from K could go to any vertex from A to I, but it could not go from J to L, because obviously there's a side going from K to L and K to J. How many diagonals does a regular 12-sided figure have, a regular dodecagon? So choose any starting vertex. For that, we have 12 choices. Step 1. Then, how many non-adjacent different vertices does it have? So if we start at A, well, for the second vertex, we can't pick A again. We can't pick B or L, which is right next to A. So there's 3 that we can't pick, so there's 9 that we can. And so that's 9 times 12, but just like the handshakes, everything's getting counted twice. Because if we say this diagonal right here from A to E, that's getting counted once as one of A's diagonals, but it's also getting counted once as one of E's diagonals. But of course, there's only one diagonal here. We don't need to count it twice. So we have to divide by 2, and so that's 6 times 9, or 54. And so there are 54 diagonals in a regular 12-sided dodecagon. This is precisely what we're doing in the previous video on repeated elements. For example, we learned in that video if 3 elements are identical, then we divide by 3 factorial, or 6, in order to eliminate repetitions. So here's a practice problem, and again, this is a practice problem you can do from the fundamental counting principle perspective. Pause the video and then we'll talk about this. Okay, from a set of 10 different identical items, Lisa is going to select 3 as a gift for someone. How many different sets can she pick? And so this is an example where order does not matter. It's just going to be a set of 3 gifts. It doesn't matter what order she picks them. So using what we've learned so far, fundamental counting principle, there are 10 choices for the first gift, 9 choices for the second gift, 8 choices for the third gift, but that doesn't take into account, that would count all the possible orders, and we don't care about orders. Because we don't care about orders, and we would have overcounted by 3 factorial, or 6, so we have to divide by that. So this is an example of the 6 different arrangements of the same 3 gifts. So all 6 of those just count as one set of gift. We don't need to count it 6 times. So the 10 times 9 times 8 is 6 times too big. So we're going to divide 10 times 9 times 8 times 3 factorial. 3 times 2, we're 6. Then we can divide out the 3, cancel the 3 with the 9, cancel the 2 with the 8 to get 4, and then go 3 times 4, which is 12, times 10 is 120. And that's the number of different sets that she could pick. In that problem, we wanted a collection of 3 items, and we didn't care about the order of items. In this video, we saw that we could calculate the right answer using the fundamental counting principle and then eliminating repetitions. In coming videos, we will learn another approach. We'll learn that this collection is called a combination, and we have other ways to calculate a combination. And I'll point out that you really understand a math problem if you know multiple ways to calculate it. In summary, when we count, we must eliminate repetitions. We do this by dividing by the total number of times each arrangement is repeated.
Combinations. This is a fun topic. So far, we have been looking mostly at problems in which we are selecting ordered arrangements. Sometimes order doesn't matter. For example, suppose from a group of 20 individuals we're going to choose a group of 3 for a team of some kind. A small group drawn from a large group is a combination. And in combinations, we don't care about the order of selection. All we care about is the final arrangement that we get. Suppose we have 6 employees of equal rank in a work group, and we're going to choose randomly 3 of them for a task. Let's say the 3 chosen are B, E, and F. All that matters is who has been selected. It doesn't matter at all which one was picked first or second. It doesn't matter if we picked B first and then F, or we picked E first, then B. It does not matter. All that matters is the resultant group. In combinations, only the final selected group matters. The order in which they were selected for that group doesn't matter at all. If we have a group of n different individuals and we randomly select R of these individuals, then the number of combinations is denoted with this notation. We read this as n choose R. Okay, so we have a pool of n and we're choosing R. For example, 8 choose 3 would be the number of different 3-person combinations we could select from a pool of 8 people. Before we discuss how to calculate this, I will point out a few things. First of all, think about what 7 choose 1 means. It means we have a group of 7 people and we're going to choose one of them at random. Well, how many ways can we do that? Well, there are 7 people, so we could pick any of the 7. There'd be 7 different ways to do it. So it's a number of ways I can choose one person from a pool of 7, so it has to equal 7. And in general, n choose 1 has to equal n. That's important idea number 1. Now think about 10 choose 4. This is the number of different 4-person combinations we could select from a pool of 10. We'll talk about what 10 choose 4 equals in a minute. For now, notice that when we create a group of 4, we also automatically create a group of 6, the 6 people left behind who weren't chosen. Every group of 4 corresponds to a group of 6, so there must be the same number of them. In other words, 10 choose 4 must equal 10 choose 6. There's a 1-to-1 correspondence between groups of 4 and groups of 6 when we're choosing from a pool of 10. And similarly, 10 choose 3 would have to equal 10 choose 7, 10 choose 2 would have to equal 10 choose 8, and so forth. In general, if we select a group of R from a pool of n, we automatically create another group of n minus R folks who are left behind. Starting from a pool of n, there must be one group of n minus R for each combination of R. Therefore, n choose R must equal n choose n minus R. That's a very important formula, and that shows a deep symmetry to these ideas of combination and these numbers that we get for combinations. Now we can discuss how to calculate 10 choose 4. Suppose we actually need the number. Think about 10 choose 4. We have a pool of 10 people, 10 different items, and we want to select 4. How many different sets of 4 could we pick? Well, with the fundamental counting principle, we'd start with that. We'd choose 10, then 9 choices for the second, then 8 for the third choice, and 7 for the fourth choice. So 10 times 9 times 8 times 7. But that would be correct if order mattered, but because order of the 4 selected didn't matter, we have to divide by 4 factorial. So 10 choose 4 is that product divided by 4 factorial. Multiply it out. We'll do a little canceling. Cancel the 9 and the 3. We get 10 times 3 times 7. So that would be 10 times 21, or 210. And so 10 choose 4 equals 210. That's how we actually calculate it. Now notice we got another one for free because, as we noted earlier, 10 choose 4 has to equal 10 choose 6. So 10 choose 4 equals 210 and 10 choose 6 equals 210 also. Here's a practice problem. Pause the video and then we'll talk about this. Okay, we have 12 different major rides. We can choose any of the 3 of them. So this is simply going to be 12 choose 3. So we just have to calculate 12 choose 3. So First we'll figure out we have 12 choices for the first one, 11 for the second, 10 for the third, and then we divide by 3 factorial because the order doesn't matter, so we're eliminating the repetitions due to the different orderings of the choices. And so 12 choose 3 would just be 12 times 11 times 10 divided by 6. Well, 12 divided by 6, of course we can cancel. We get 2 times 11 times 10, that's 22 times 10, or 220. That's how many sets of 3 rides we can do, and that is the number equal to 12 choose 3. Incidentally, it would also be the number for 12 choose 9. Sometimes in the more advanced problems, you may need to know the abstract combinations formula. This is the abstract formula. And this formula is designed to have a massive amount of cancellation in it. But I will say the formula is clunky. After a lot of cancellation, all that reduces to the much simpler fundamental counting principle approach that we were already using. So this is one case in which if you're eager to memorize a formula, don't. This formula is not very useful. It would only be useful in a question that we're asking very particularly about the formula. Yes, that could happen. On a very advanced question, they could actually ask about the formula itself. Most practical combination questions, such as the ones we've done in the video, it's much easier to use the fundamental counting principle. And in fact, problems like this in some way are designed to punish the people who blindly rely on formulas rather than understanding more mathematical approaches to the problem. In summary, in a combination, we're concerned with an end group of R individuals chosen from a pool of n, and the order of selection does not matter. N choose R is the number of ways to choose R individuals from a pool of n. N choose 1 has to equal n. N choose R always has to equal n choose n minus R. That's a very important symmetry formula. And we can calculate n choose R by starting with the fundamental counting principle and then dividing to eliminate repetitions. When to use combinations. This is a tricky issue. We use combinations when order doesn't matter. Okay? But what exactly does it mean for order to matter or not matter? Many students are confused on this issue of whether order matters in a particular problem. Before we address the question of whether order matters, let's be clear about why we're asking it. If order matters in a problem, then most likely we'll break the selection problem into stages, count the possibilities in each stage, and use the fundamental counting principle, just the straight fundamental counting principle. If order doesn't matter, it's a combination. And we will use the combinations approach, that is, start with the fundamental counting principle, but then we divide off the repetitions. So this whole business of whether to not to divide off the repetitions, we divide off the repetitions if order doesn't matter. So suppose we have a problem in which we have a pool of 20 committee members, and for the leadership team we're going to pick 3 officers, a chairman, a treasurer, and a secretary. Does order matter? Some students might be tempted to say no, because of course it doesn't matter whether we pick the chairman first or the secretary first, but that's not the right way to think about the question of whether order matters. One way to think about it is to be results oriented. In other words, look at the group that results from the selection. If we can swap around the members of this selected group and this meaningfully changes the outcome, then order matters. For example, in this problem, suppose we got a leadership team of B as the chairperson, N as the treasurer, and F as the secretary. If we swap around the roles, make F the chairperson, B the treasurer, and N the secretary, well, that's a different leadership team. In other words, different people in different roles, that's a real difference. That's a meaningful difference. So order actually does matter here. Because order matters, we would just use the ordinary fundamental counting principle. 20 for the first choice, then there'd be 19 left for the second choice, then there'd be 18 left for the third choice. And so that would be the answer. We're not going to calculate that right now. That's a larger number. And in fact, the test might not even have you calculate that. The test might just leave it in a form of factors like that. But the point is, once we determine that order matters, then we break the problem into stages, calculate the number of options at each stage, and employ the fundamental counting principle, and we're done. That's the answer. Suppose a chef is making a soup, and he has 20 vegetables from which to choose. He's instructed to choose any 3 vegetables, cut them into small pieces, and stir them into a large pot of soup. How many different soups could he make? Well, we're assuming that the soup is determined purely by the choice of vegetables. Well, here it doesn't matter at all which vegetable is picked first or second or third, because they will all be cut into small pieces and stirred together. So it's absolutely irrelevant. You're just going to have small pieces of one floating next to small pieces of the other. It doesn't matter the order at all. They all wind up in the same pot. Because order doesn't matter, it's a combination. So this would be 20 choose 3, which would be 20 times 19 times 18 divided by 3 factorial. 3 factorial, of course, is 6. We'll do a little canceling. 3 times 19 is 57. So we had 20 times 57. Well, 20 times 50 is 1,000, and 20 times 7 is 140. So this would be 1140. And that would be the total number of soups. These were 2 examples, but there is tremendous variety in counting problems. Notice there is no clear-cut black and white rule that you can always use to determine whether order matters. I've given you some guidelines, some ways of thinking about it, but there's not a black and white rule system where you can always determine yes, order matters, no, order doesn't matter. Ultimately, determining whether order matters is what traditionally has been called a right brain skill. What does this mean? Well, according to that paradigm, the left brain is analytical and logical. The left brain loves clear rules and procedures. The left brain's question is this: what is the right thing to do? The left brain loves nothing more than just an absolute fixed, clear recipe. Give me an unambiguous recipe that I can follow. That's what the left brain loves. The right brain is said to be the world's best pattern matching device. The right brain is nonlinear and holistic. We dream with our right brains, for example. The right brain question are these: what is the right way to see the problem? What is the right way to look at the problem? Or in other words, what is the right way to frame the situation? In counting problems, once you look at the problem the right way, what to do becomes easy to see. With counting problems, it's very important to study the solutions looking for how to see. That is, what was the right way to look at the problem? What perceptual choices did the author of the solution make at the very outset of the counting problem? So that can be one of the harder things to observe about a solution, especially if you're rushing through just to, well, what should I do? What should I do? Then you miss the most important part. The most important part is, well, how did they frame it at the very outset? How did they dissect it before they started doing anything? Here's a practice problem. Pause the video and we'll talk about this. Okay. A classical concert will consist of 2 overtures in the first half and 1 symphony in the second half. The symphony and 2 overtures determine the program. Conductor can choose the program from 10 possible overtures and from 6 possible symphonies. How many programs are possible? Well, let's think about the overtures first. For the overtures, there are 10 choose 2 possibilities. Well, that is 10 on the first choice, 9 on the second choice. We divide by 2. That's 5 times 9, which is 45. So there are 45 possible pairs of overtures that could be picked. And then there are 6 possibilities for the symphony in the second half. So we have the 2 overtures and the symphony, and it means multiply. So it's going to be 6 times 45. We can use some doubling and halving. That's 9. That's 3 times 90. 3 times 90, of course, would have to be 270. There are 270 possible programs. Here's another practice problem. Pause the video for a minute, and then we'll talk about this. A librarian has a set of 10 books, including 4 different books about Abraham Lincoln. The librarian wants to put the 10 books on a shelf with the 4 Lincoln books next to each other somewhere on the shelf. How many different possible arrangements of the 10 books are possible? This is a hard question. Since the 4 Lincoln books must be together, let's start out by thinking of them as one big book. There are 6 books in one big Lincoln book. How many different ways can we put these 7 books in order on a shelf? Well, of course, 7 factorial. That method of counting gives us a position for the Lincoln books among the other 6 books, but we still can put the 4 Lincoln books in any order. There are 4 factorial orders for the Lincoln books, so the total number of arrangements is 4 factorial times 7 factorial. That's answer choice C. Notice, incidentally, we can't simplify that any further. We have to leave that as 4 factorial times 7 factorial. In summary, if order matters, we break it into stages and just use the ordinary fundamental counting principle. If order doesn't matter, we use the combinations approach. One guideline is to consider the resulting arrangement and whether switching items around in this result would matter, whether it would meaningfully make some kind of different arrangement. That's one possible guideline to use. And of course, you should read the solution sets and study how the instructor chooses to view the situation. In other words, what perceptual choices did the person writing the solution make in order to frame the question, in order to analyze it before they started doing any calculations.
Here we'll talk about calculating combinations. So suppose we have determined that we need to use a combination in a particular question. And if this is something that you're trying to determine, the previous video talked about how to determine whether to use a combination or not, whether order matters or not. Here we're just going to talk about, suppose we've already determined, okay, order doesn't matter, it is a combination, how do we get the number? Here we're focusing on getting the actual number. Now I'll say that sometimes answer choices will be written in the form of, say, 5 choose 10. So we won't actually have to do the calculation, and that typically most happens when the combinations are very, very large. The test will just list answer choices in that form, something choose something, and we don't have to do any combination, any calculations. We simply have to recognize. More often, though, we do need to calculate combinations. First of all, remember that the formula, the way that it's set up, it looks like it requires a massive amount of calculation. There are 3 factorials there. If you ever make the mistake of calculating the 3 factorials separately, you'll be making the problem much, much harder for yourself. And so in that sense, the formula can be misleading. Using this formula is much more efficient if you remember that the larger factorial on the bottom, whichever one of those 2 is larger, will always cancel. That's always the way to begin using this formula. And so just as an example, I'm going to calculate that combination that I had on the first slide, 50 choose 10. Now this would be much larger than anything the test would expect you to calculate, but I'll show this just for the sake of an example. So first of all, plugging into the formula, we get 10 factorial, we get 50 factorial over 10 factorial times 40 factorial. Well, of the 2 factorials in the denominator, 40 is bigger. Now let's think about this. 40 factorial, that's the product of all the numbers from 40 down to 1. 50 factorial is the product of all the numbers from 50 down to 1. Well, included in that, we'd go from 50 down to 41, and then starting at 40, it would be 40 factorial. And so 40 factorial immediately cancels. And so what we get, once we cancel 40 factorial, we get all the numbers from 50 down to 41. Everything below 41 has canceled, so that's left in the numerator. And in the denominator, we're just left with 10 factorial. And now we're going to do a little more cancellation. And so basically, you want to cancel as much as possible before you do anything else when you're using this formula. In other videos, we've talked about cancel before you multiply as an important rule. Here it is a paramount rule. You have to cancel before you start multiplying. So first of all, we can just cancel the 50 with the 5 and the 10 in the denominator. Then we can cancel the 42 with the 6 and the 7. Then the 8 times 3 times 2, or 8 times 6, that cancels 48. We'll divide 45 by 9, leaving us with 5. We'll divide 44 by 4, leaving us with 11. Now we could rearrange the order of those factors, but basically the test might expect you to simplify down to that. Now, no one is going to expect you to come up with this answer here. That's the actual answer when we multiply everything out. So this is just an example of how to cancel. And again, this is a much, much bigger one than anyone would expect you to calculate. The approach we have recommended in previous videos is much more efficient. Begin with the fundamental counting principle and then divide to eliminate repetitions. Remember to cancel before you multiply. Remember to leave all products unmultiplied until all possible canceling is done. I will also show a couple other ways to think about calculating combinations. One shortcut involves the case of n choose 2. That is a case in which we are picking an unordered pair from a larger set. Let's think about this with the fundamental counting principle approach. We have n choices for the first item and then n minus 1 choices for the second item, but because order doesn't matter, we have to divide this product by 2 because each pair would be counted twice. And so we get n choose 2 equals n times n minus 1 over 2. And that's just a handy formula to know. You may remember from the sum of sequence videos that this is also the sum of the first n minus 1 positive integers. It's worth remembering that this shortcut pattern shows up in a couple different areas of mathematics. And if you haven't seen that video, that would be a helpful video to watch, and it might help you remember this as well. Another mathematical pattern that is directly related to n choose r is Pascal's triangle, named for Blaise Pascal. And so here's Pascal's triangle. It's often something that they have little kids create because everything is just created by addition. If you notice, every number is the sum of the two numbers diagonally above it. For example, 3 is 2 plus 1. 6 is 3 plus 3. 4 is 3 plus 1. 10 is 6 plus 4, etc. Once you have any row across, it's very easy to find all the rows underneath it. So the two outside diagonals are always the ones, and again, all the inside numbers are the sum of the two numbers diagonally above it. Pascal's triangle gives all the values of n choose r. In fact, n choose r is the entry in the nth row at the rth place in Pascal's triangle. The tricky thing about this is we need to remember to start counting rows and places from 0. The top one is the 0th row, 0 place. 0 choose 0 equals 1, but that's not very meaningful in real-world combinations. You know, if you have nothing, how many different ways can you pick nothing? I guess, you'd have one way of picking nothing, It's not very meaningful. In any row below the first one, the second number in the row gives you the row number. It's often a very good shortcut to have row 3 memorized. So 1, 3, 3, 1. That's a really good place to start. It's a good starting place. And from there, we can generate several more rows very easily. So for the fourth row, we have the ones on the outside. 3 plus 1 is 4. And of course, that doesn't surprise us because we have to have 4 as the second number in the fourth row. And of course, it's symmetrical. It's 100% symmetrical. So when we add it on both sides. And then, of course, 3 plus 3 is 6. So now we have the fourth row. Now we can get the fifth row. 1's on the outside. 1 plus 4 is 5 on both ends. 4 plus 6 is 10. So we get two 10s in the middle. Now we can get the sixth row. 1's on the outside. Then we get 6's. Then 5 plus 10, 15. And then in the middle, 10 plus 10 is 20. Now the seventh row, we have 1's on the outside. 1 plus 6 is 7. 6 plus 15 is 21. And 15 plus 20 is 35. So we'll stop there, but let's see what we have now. This is the seventh row of Pascal's triangle. Well, the first entry, 7 choose 0 is 1, is not very interesting. If you have 7 things and you choose none of them, how many ways can you do that? That's not interesting in real world terms. Then, of course, 7 choose 1 is 7. If we have 7 unique items, how many different ways could I pick one unique item? Well, 7 of them. But then the meaningful combinations, 7 choose 2 is 21, 7 choose 3 is 35, 7 choose 4 is 35, 7 choose 5 is 21, 7 choose 6 is 7, and of course 7 choose 7 is 1. And so we get all of those numbers all at once, all the way across the row. And you can see if you had a problem where you had to compute 7 choose 2 and 7 choose 3 and say 7 choose 5, if you had to compute all these numbers, it might just be easier to calculate the row of Pascal's triangle, and then you have all of these numbers automatically. If you practice constructing Pascal's triangle, you'll get quick at it. And again, this is something they have kids in grade school do, so it's not actually very hard to create Pascal's triangle. And so if you practice it, especially start with row 3 and practice it, you can get very, very quick. Then you can just jot it down at the beginning of the quant section, and you'll just have it if you need it. If in a problem you have to figure out different size combinations from the same pool, say 8 choose 3 and 8 choose 4, then it may be quicker to draw Pascal's triangle down to that row rather than to do all the separate calculations. In summary, remember that you can always calculate combinations by using the fundamental counting principle and dividing to eliminate the repetitions. Remember to cancel in the n choose r formula, including canceling before you multiply. Remember the shortcut formula, which also appears in sums of sequences, and practice using Pascal's triangle to generate values of n choose r. Now we can talk about permutations. And if you've been watching all the counting videos in order, the funny thing is permutations have already been covered. We just haven't used the word. In fact, using the fundamental counting principle is almost always a much more efficient way of handling a permutation problem, much better than using the formula. And so, if you haven't seen the video on the fundamental counting principle, I'd highly recommend watching those before you watch this video. The fundamental counting principle is the most important principle in all of counting. If you're already comfortable with calculating everything from the fundamental counting principle, then you don't even need to watch this video, although it always helps to have more than one way to review and think about things. If you are not familiar with the other lessons about the fundamental counting principle, again, I highly recommend that you watch those videos before you watch this one. This one will not make a lot of sense if you're not familiar with the fundamental counting principle. One very useful formula, and this is one of the few that it's really worthwhile memorizing, is that if we have n different items and we're going to permutate all n of them, we're going to take n items and put them in as many orders as possible, that's n factorial. That's a useful formula to know. For permutations of k items selected from a larger pool of n items, don't memorize a formula. Instead, use the ideas of the fundamental counting principle. And I want to emphasize here that knowing a formula is not the same as understanding math. Sometimes people think if they memorize all the formulas, they really have a handle on the math. Sometimes memorizing the formula actually impedes your understanding of math, because then you're relying exclusively on the formula rather than understanding everything about the mathematical situation. And so beware of formulas. They're useful in some ways, but don't be over-reliant on them. Here's a permutation problem. Pause the video and then we'll talk about this. From a group of 10 committee members, 3 will be selected randomly. 1 is chair, 1 is treasurer, 1 is secretary. These 3 will form the quote-unquote board of the committee. How many different possible boards can be formed? So for this one, what we're going to do is, instead of using a formula, we're just going to say how many choices for the first person, 10 choices, how many choices for the treasurer, 9 choices, how many choices for the secretary, 8 choices. And we're just going to multiply 10 times 9 times 8. Well, 9 times 8 is 72, times 10, 720. And so we get this directly from the fundamental counting principle without using any formula at all. And that's very important. So that problem was a permutation because, quote, order mattered. In other words, if we pick person A as the chair and then person B for the treasurer, picking them in a reverse order where person B is the chair, person A is the treasurer, that would be a different board. So swapping the people around in a different order actually results in a different board. We know that we use permutations when order matters and combinations when order doesn't matter, but what does it mean for order to matter? How can we decide? And the difference between order matters and order doesn't matter is not simple. There's not a clear, hard and fast rule that we can say, okay, if this is true, then order always matters. If this is true, order never matters. The trouble is that whether order matters or not is fundamentally a right brain question. It's a question about patterns. It's not a logically, follow the recipe kind of question. Left brain is always concerned with what is the right thing to do. Left brain wants a recipe. Give me a clear recipe and I know what to do. That's the left brain. The right brain is about the right way to look at a question. What is the right way to look at a problem? And if you get into that right brain mode, if you look at a problem the right way, then what to do becomes very easy once you're looking at it the right way. And whether order matters or order doesn't matter is very much about the right brain. So it can be a challenge for people who are habitual rule followers and want to rule for everything. So I'll give you some guidelines about order. There are no hard and fast rules, but some general guidelines. If we're counting the number of physical arrangements, so we're putting books on a shelf or children are sitting in a physical row of chairs, then of course order matters because there's actually a physical place for each thing, and swapping two things in two different places will give us a different order. If roles are specified for each choice, for example, the problem we just had, where each role there was a treasurer, there was a chair, there was a secretary. If there are specific roles for each slot, well then order matters also. If choosing elements in different order produces different meaningful outcomes, then order matters. And often it's helpful just to think, as you're thinking through a problem, what would a few choices look like? And usually it's not possible to list out every possible choice, but if you list out a few, it gives you a sense of the patterns. Conversely, if choice of individual elements doesn't make any meaningful difference in the final set, then order doesn't matter. So for example, if we're looking at the sum of 3 dice, I roll 3 dice and I'm just finding the sum. Well, order doesn't matter. It doesn't matter which dice hit the ground first or anything like that. All we're doing is we're adding the sum of the 3. And so one dice had a 2 and another dice had a 6. If we swap those two, we'd still get the same total. So order doesn't matter. Similarly, if there are 10 colored balls and I'm going to pick 3 and put them in my pocket, well, once they're in my pocket, they're all going to be mixed up anyway. And so order doesn't matter. The order in which I pick the balls does not matter. And so you very much have to think about patterns, and you have to think about the actual situation to determine whether order matters or not. Finally, as an overview, permutations versus combinations versus the fundamental counting principle. Remember that the fundamental counting principle is more basic, more flexible, and more widely applicable than either permutations or combinations. And in fact, all the rules of counting, including the permutations formula, including the combinations formula, all of them come from the fundamental counting principle. If you're picking with no repeats and order doesn't matter, then we can use combinations. If you're picking with no repeats and different orders of the final section are meaningfully different, then it's a permutation. Use the fundamental counting principle. And if there are repeats, for example, if we're picking out of a deck or something, and then each time we pick, we shuffle the card back in the deck, and so we could repeat. Any situation like that, then we'd have to use the fundamental counting principle. In other words, if the situation is at all outside of the box, then the combination and the permutation lens is not going to be the appropriate one. You're going to have to go to the much larger lens of the fundamental counting principle.
Counting strategies. In this lesson, we will simply review all the counting strategies that we've studied in this module. First of all, remember that in counting problems, AND means multiply and OR means add. That's a very simple but big idea. Remember that listing possible outcomes will rarely solve the problem, but doing so can give you some idea about how to proceed. So it can give us a sense of which method we're going to use. If you can break the problem into stages, then you can apply the fundamental counting principle. Remember to count the most restrictive stage first. We can put n different items in order in n factorial different arrangements. If some of the elements are identical, we divide by the number of identical elements. In general, if our counting approach produces repetitions, we divide to eliminate repetitions. Remember to use combinations when order doesn't matter. Remember that we have multiple ways of actually calculating the combinations. Remember that permutations are just another way of talking about the fundamental counting principle, and it's much easier to solve those using the fundamental principle than learning a new formula. In general, throughout all math on the test, knowing formulas is not a big part of what you need to know. In fact, knowing formulas constitutes probably about 10% of what you actually need to know to be successful on the test. In counting problems, in combinatorics, knowing the formulas alone is about 2% of what you need to know. In other words, if you know the counting formulas and that's all you know almost nothing. You need to know things like the fundamental counting principle, counting with using restrictions, what if there are repetitions, all the things that we've talked about in this module. These are more important than memorizing formulas. A very left brain approach to the quant section is to memorize formulas and rules and procedure. That approach will yield only limited success in counting problems. As discussed a few times in these videos, counting is a much more right-brained area of mathematics. The left brain question is, what is the right thing to do in this problem? The right brain question is, what is the right way to look at this problem? What is the right way to frame the information? What are the right perceptual choices to make in order to dissect the problem? More so than in any other math problems, it's important to read solutions to all counting problems. Even if you get them right, read the solution or watch the explanation video. When you read these solutions, don't simply focus on what to do, because then you'll be left with that question, why did they do this instead of that? Instead, focus on how the solution framed the problem, noticing the perceptual choices the solution made at the very outset. As you study solutions in this way, you observe patterns, and it's by learning these patterns that you develop a deep understanding of combinatorics.